Everybody, welcome back. We are about to start a new chapter. This will be chapter 4 that we're talking about today. And I'm going to jump right into it with a definition in just a minute. But to set the stage, here's what we've done so far. We've studied this place called Rn. Rn is a collection of column vectors, and with these column vectors, well, there's a couple of operations we can do. We can do scalar multiplication with column vectors. We can also do addition. We can add two column vectors together. And then Rn comes with a bunch of properties, right? Associative property, and there's some distributive properties, and so on. What this definition is about to do is generalize this idea. So definition: a vector space is a set, which I'll denote with a capital V, whose elements are called vectors. Together with two operations called scalar multiplication and vector addition. That satisfies the following properties for all u, v, and w in V and scalars. R and S, let's say. Okay, so I need to write down some properties, and I'm going to do that in just a second. So let's just notice what we have here, right? Previously, when we said the word vector, we meant a column that had some real numbers as entries. What we're doing now is we're generalizing this idea of vector so that Rn is going to be one special example of a vector space. So we're creating, or this definition is going to capture the properties that we've seen in Rn. What can you do with vectors now? You can add them and you can multiply them by scalars. And we are going to see that there are many, many other objects out there that can serve as vectors, not just these things that we write as columns. Okay, so let's write the properties down. So this definition is kind of long-winded. The first property, u plus v is in capital V. So if you take two vectors and add them together, you get another vector. What we say is that V is closed under addition. Right? So when we say it's closed, what we're saying is that when you perform the operation of addition on a couple of vectors, the result is another vector. The second property, R times U is in V. Oh, I should point out here, notice I'm writing arrows over the U, the V, and the W, just as I did before when we were talking about columns. So when we discuss vectors, I will put little arrows, your book will put bold-faced, or will bold-face the letters, right? So those are the symbols that we'll use for vectors. So here we go, back to here, R times U is in V. This can be, or the words that we say here, V is closed under scalar multiplication. So those are the first two properties. The next property, commutativity. So U plus V is equal to v plus u. It does not matter what order you add vectors, you'll get the same result. So this is commutativity. Or let's just say addition is commutative. That's easier to write. Addition is commutative. Fourth property, u plus v parentheses plus w is equal to u plus v plus w. Here, what do you call this property? This is associativity. So addition is associative. Property 5. There exists an element which we will write as boldface 0 in capital B, such that 0 plus v, I guess I should use u, 0 plus u is equal to u. This element right here, 0, is called an additive identity. So let's just say here in parentheses, v has an additive identity. Number 6, there is an element which we'll write as minus u, such that u plus minus u is equal to the 0 vector. You can say this in words, every element has an additive inverse. That's a special word, or a special word for saying it's got a negative. Okay, so that was property 6. Property 7. And there's actually a couple of distributive properties, so let me write these out. The first one, r times u plus v is equal to r times u plus r times v. And there's also, so this is number 8, also in a distributive property, r plus s times u is equal to rs, ru plus su. So these two properties are distributive properties. How much room do I have? I guess I got a little bit more room down below. I need to fit 2 more of these in here. So number 9, rs, what do I have? Rs times u equals r times su. And then property 10, which I think I can just squeeze right over here, 1 times u is equal to u. I don't have nice names for properties 9 and 10. But let me just check. Does that fit in the shot? Yeah, you can see that. Okay. All right. So this is there's a lot to this definition right here, right? A vector space is a set together with a couple of operations that satisfy a bunch of properties. And if you notice, I don't have the properties memorized in order. I know which each one of these properties are, and I know them by name rather than, oh, I remember property 3, right? So I just remember, yes, vector addition is commutative, vector addition is associative, and so on. So when it comes to learning these properties, these are really more common sense properties. These are properties that hold in Rn, right? This generalizes the idea. One thing to note here, and I'm going to write this down before I erase everything. So scalars are usually in Rn. All right, so typically when we do scalar multiplication, right, this operation right here, R, the constant, comes, oops, not from Rn, sorry, from R, not Rn. So scalars usually come from R. Occasionally, from the set C of complex numbers. So occasionally we will talk about complex scalars. Okay, so let's jump into some examples. And the first obvious example Rn is a vector space under the usual operations of vector addition, where you add two column vectors, and scalar multiplication. We already know this is true. So I'm not going to go through the verification of this. I want to do a more interesting example. And so the idea that I want to get through is that this notion of vector space is modeled on our knowledge of Rn. Right? Our understanding of Rn motivates this whole process. So here's the example, and I'm going to work this one out in full detail. So let's let P sub n be the set of all polynomials of degree less than or equal to n. So we're going to show that appropriately defined, Pn, this set right here, is a vector space. The collection of all polynomials satisfies all the properties of vector space. Now I need to define, so we're going to define addition and scalar multiplication as usual. Right? And now, so what does that mean? So if, I just want to get familiar with writing this out. So let's see, we're going to have a couple of polynomials. So let's say we have P of x. That will be a0 plus a1x plus dot dot dot. Up through a, we're doing degree n. Okay, so this will be a sub n, x sub n. And q of x equal to b0 plus b1x plus dot 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 plus bn x to the n. So I just want to remind you, how do you add polynomials and how do you multiply polynomials by a scalar? So then p of x plus q of x is equal to a0 plus b0 plus a1 plus b1 times x plus dot 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 plus an plus bn times x raised to the n. So here's our definition of vector addition. When you add two polynomials, the polynomials are serving as vectors. Right, here's the usual formula. And let's say we have some real number r times p of x. That's equal to ra0 plus ra1 times x plus dot 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 plus r a sub n x to the n. Okay, I need to verify that, or I want to go through all the details, but verify that p sub n, this set of polynomials of degree less than or equal to n, actually satisfies all the axioms, all the properties of being a vector space. So first, remember, properties 1 and 2 are closure properties. And so we want to say, all right, if we take two polynomials and add them together, what do we get? Well, if we start off with polynomials whose degrees are less than or equal to n, when you add them together, notice what you get. You get a polynomial of degree less than or equal to n. Also, if you take a polynomial of degree less than or equal to n and multiply it by a real number, what do you get? You get a polynomial whose degree is less than or equal to n. So that tells us that properties 1 and 2 are satisfied. Closure is satisfied by definition. So 1 and 2 satisfied by, I'll say by construction. Our definition of polynomial addition and scalar multiplication here satisfy the closure properties. Property 3, that's commutativity. Well, let's just write this out. So p of x plus q of x is, as I have written down here, a0 plus b0 plus a1 plus b1 times x plus dot 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 plus plus a sub n plus b sub n x to the n. Now, this is exactly equal to b0 plus a0 plus b1 plus a1 times x plus dot 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 plus bn plus a sub n times x sub n. What property am I using here? I'm using the fact that if you add two real numbers, it doesn't matter what order. So addition of real numbers is commutative, and what that does is it shows us, right, this is q of x plus p of x, so it tells us addition of polynomials is commutative also. The next property, associativity. So let me write it like this. So if I need a third polynomial here, so p, q, r, s, t, let's call it t, I guess. If t of x is the polynomial c0 plus c1x plus dot 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 plus c sub n x sub n. So if I have another polynomial, then the ith coefficient of p of x plus q of x in parentheses plus t of x is, so when you add these polynomials and you look at the coefficient corresponding to x sub I, it's going to be c, no it's not, it's going to be a sub 0 plus, a sub I plus b sub I parentheses plus c sub I. This, because addition of real numbers is associative, this is equal to ai plus parentheses bi plus ci. And this right here, this is the coefficient. So this is, which equals the coefficient of the polynomial p of x plus parentheses q of x plus t of x. Right? So if you do this order of addition versus this order of addition. Here are the coefficients you get, but these are equal because of associativity of addition of real numbers. Okay, so what's our next property now? I want to check property 5. Let's say it like this. We have the 0 polynomial. That's just a constant polynomial, 0, right? 0 plus p of x is definitely equal to p of x. Property 6, so we need a negative, an additive inverse, minus p of x equal to negative a0 plus negative a1x plus dot 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 plus negative a n raised to the, or times x raised to the n, satisfies p of x plus negative p of x equal to the 0 polynomial. And I'm just going to emphasize that it's always got to be the 0 vector. In this case, the 0 vector is the 0 polynomial. So here, the 0 polynomial. Then we've got a couple of distributive properties. So let's see if I do r plus s, other order, r times p of x plus q of x. That's going to be r times a0 plus b0 plus a1 plus b1 times x plus dot 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 plus an plus bn x raised to the n, close parentheses. And then if we distribute here, so now let's think about, we know how to do this right here. This is going to be r times a0 plus b0 plus r a1 plus b1 x plus dot 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 plus r an plus bn x. Now I want to use the fact that multiplication, or well, let's say it this way, real numbers satisfy a distributive property, right? The operations of multiplication and addition of real numbers satisfies the distributive property. So this is r times a0 plus r times b0 plus r a1x plus r b1x plus dot 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 plus r an plus r an x to the n plus r bn x to the n. And now if I join all the stuff that involves the a's in one's place, what we'll have is r a0 plus r a1x plus dot 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 plus r an x to the n plus r b0 plus r b1 plus dot 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 plus r bn x to the n. And that is r times p of x plus r times q of x. Right, so that tells us that property 7 is satisfied. Property 8. Let's see now. If I do r plus s times p of x, that will be r plus s times a0 plus r plus s a1x plus dot 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 r plus s a sub n x to the n. That's just the definition of scalar multiplication. Now, if I multiply things out, this will be, and I'm going to kind of, we know how to do the distributive property here. This is r a0 plus s a0 plus r a1x plus s a1x plus dot 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 plus r a n x to the n plus plus s a n x to the n. Separate these into two pieces now, so this will be r a0 plus r a1x plus r a n x to the n plus s a0 plus s a1x plus dot 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 plus s a n x to the n. And now what do we have? Well, the first piece we're looking at r times p of x, and then the second one is s times p of x, right? So property 8 is satisfied. I know this computation gets a little bit tedious, but you should just, one time you need to work through it so you understand how this goes. We're going to learn ways to sort of shortcut some of the axiom checking, but everyone needs to go through it a few times in their life. So two more axioms. So number 9, if I do rs times p of x, that's going to be rs a0 plus r, I'll put the parentheses here, rs a0 plus rs a1x plus dot 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 rs a n x to the n. Now, multiplication of real numbers is associative. So I can slide these parentheses. And now I can factor an r out of the entire thing. Let's see, this will be an s a n x to the n, and that is r times s p of x. All right, and then there's one more property, property 10. If I do 1 times p of x, well, I'm going to go through the whole thing here. So 1 times a0 plus 1 times a1x plus dot 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 plus 1 a n x to the n. 1 times any real number is that real number, so this is a0 plus a1x plus dot 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 plus a n x to the n, which is p of x. We have verified all 10 properties of vector spaces. That tells us then, so our conclusion, P of x is a vector space. Oh, sorry, not P of x. P sub n is a vector space. This will be an important vector space. This will show up lots and lots of times in this class. All right, let's do some more examples. The next example I want to look at, let's let m sub mn, so capital M and then a double subscript little m little n. I want this, let this be the set of all m by n matrices under the usual operations of scalar multiplication. and addition. Right, so back in chapter 1, we talked about what it means to do scalar multiplication with a matrix. We talked about what it means to add two matrices together. So now I want to take the set of all of them, and it turns out this set right here, under our usual operations, forms a vector space. Now, I don't want to go through all the gory details again, so I'm going to say check that M sub mn is a vector space. Let's just kind of talk our way through some of the properties though. So let's see, if you add two m by n matrices together, the result is an m by n matrix. What does that mean? That means that M sub mn is closed under addition. Same thing, if you do scalar times m by n matrix, you get m by n matrix, which means that M sub mn is closed under scalar multiplication. Properties of associativity and commutativity, we've already seen those. Those are properties of matrix operations. What else do we have? Oh, the zero matrix. This is one that we should mention. So in M sub m by n, when we write 0, with a bold-faced 0 in the book or an arrow over for me, what we mean is the matrix that has zeros everywhere, right? So the additive identity is the zero matrix. And of course, if you do 0 plus the m by n matrix A, right, you're guaranteed to get the m by n matrix A. And you can work through the distributive properties. We've already seen that those hold. 1 times a matrix is going to be that matrix, and so on. So it's worthwhile to go through and actually check each of these formally. And it turns out then that we've got a vector space here. Next example. And I'm going to try to follow the book's notation here. So this is f parentheses minus infinity to infinity. This is the set of all functions. So this is all functions. So let this be the set of all functions little f from R to R. And it turns out under the operation, so now we need to say what it means to add functions. So f plus g of x equals f of x plus g of x, and r times f of x equals r times f of x. So under these operations, capital F minus infinity, positive infinity is a vector space. This is worthwhile. I'm just going to write this as exercise. In fact, maybe I'll assign this one as a homework problem. Right? It's worthwhile to go through this and check all the axioms. Oh, and I said is a vector spaces. I should have said is a vector space. Okay, next example. Let's call it, I'm going to call it U, capital U. Let's let U equal the set of all column vectors x, y, such that both x and y are greater than or equal to 0. So notice in this case, U is a subset of R2. In fact, we can draw a picture. U is the first quadrant, including both the positive and positive x-axis and positive y-axis. So here's a picture of script U. So let's see. Note that, for example, the vector 1, 1 is in U, but if I do minus 1 times the vector 1, 1, that's equal to negative 1, negative 1. So this is not in script U. What does that tell us then? It tells us that our set U right here is not closed under scalar multiplication. So, U is not a vector space. Why not? U is not closed under scalar multiplication. As soon as it fails one axiom, it's all over. Right? It's no longer a vector space, or it can't be a vector space. Let's do another example. So let's say, call it Qn be the set of polynomials of degree n. This is different than our set Pn, which we showed was a vector space. Pn was the set of all polynomials whose degree is less than or equal to n. Now we want to look at the set of polynomials whose degree is exactly equal to n. So note that, let's say, let's call it P of x. And that's going to be a0 plus a1x plus dot 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 plus an x to the n, and q of x equal to, it doesn't really matter here. I'm just going to use any b0 plus b1x plus dot 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 plus. Now, what I want for this last coefficient here, I want minus a sub n x to the n. So this polynomial, I don't care what the a's are as long as they're non-zero. Well, at least an has to be non-zero. So let's say where, I should put this in parentheses, where a sub n not equal to 0 are in Q sub n. So I've got a couple of polynomials of degree n, but P of x plus Q of x, this is going to equal, well, what's it going to be? It's going to be a0 plus b0 plus dot 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 plus, now what happens when we add, the an and minus an cancel out, and so what we get is a sub n minus 1 plus b sub n minus 1 times x to the n minus 1. This is a polynomial whose degree is not equal to n, so this has degree strictly less than n. So what does that mean? It tells us that q sub n is not closed under scalar multiplication. Okay. I just erased my border here. So conclusion. Qn is not a vector space. And why is that not closed under addition? It's also not closed under scalar multiplication because you can multiply by the 0, right? You can multiply p of x by 0. And what do you get? You get a polynomial, you get the 0 polynomial whose degree is definitely not equal to n. I want to do one more example. So let's let capital V be the set of all ordered pairs. So these are elements of R2. Remember, sometimes we write our elements of Rn as column vectors, but we can also write them as parentheses. It saves space, and so I'm going to do it this way just to just so we can get used to it sometimes or somehow. So let's look at this set right here. V equals the set of all ordered pairs x comma y, such that x and y satisfy this. So this is a subset of R2. And I want to use the usual operation. So under the operations, inherited from R2. And so let's go through the axioms and see what happens here. So if x and y, or x comma y and z comma w are in V, then let's see. Well, x and y satisfy this equation, which means that x equals negative 2y. Same thing with z and w. So you say and z is equal to negative 2w. So if we do x comma y plus z comma w, that's going to equal x plus z comma y plus w, which is equal to, well, let's see now. This is negative 2y minus 2w, comma, y plus w, which is equal to negative 2 times y plus w, comma, y plus w. Now remember, property 1 is closure under addition. So when I take two elements in capital V and add them together, I need the result to be in capital V. How do you decide whether the result is a capital V? You check to see whether it satisfies this equation. So if I take the first and add it to 2 times the second, let's see what we get. So since negative 2, I mean this is sort of obvious now, negative 2 times y plus w plus 2 times y plus w equals 0, x comma y plus z comma w is in capital V. So this set, capital V, is closed under addition. Okay, so now we need to show closure under scalar multiplication. So let's say similarly, if I do r times xy, that's going to be rx comma ry, which equals, now let's see, what is rx? Well, x is negative 2y, and so this will be negative 2ry comma ry. This is what happens when we do scalar multiplication. If we want to show that we're closed under scalar multiplication, I need to argue that this element right here is inside V. How do you check that? You add the first coordinate to times plus, so you take the first coordinate plus 2 times the second coordinate. If you get 0, then you conclude that you're in V. So now we do, so we can say since negative 2ry plus 2 times ry, well that's obviously equal to 0, r times xy is in capital V. So we've shown that V is also closed under scalar multiplication. All right, now let's think about property 3. Property 3, that's commutativity. So if I take two elements of R2 and add them together, it doesn't matter what order we do it. We already know that Rn is a vector space. So there's nothing to check here. We already know. That's a terrible check mark. We already know that addition of vectors in R2 is commutative. And so if I choose these guys, these are in R2, right? Doesn't matter what order we do. Same thing with associativity. This follows because addition of vectors in R2 is associative. Property 5. Right, we need an identity. And this right here will satisfy as an identity. So this is in V, right? Because 2 times 0, what am I saying here? Oops. 0 plus 2 times 0 is equal to 0. That's what I'm saying. Property 6. Let's see, who will the negative of somebody be? Well, if xy is in B, then we look at minus x minus y satisfies negative x plus negative 2y equals 0, right? If x plus 2y is equal to 0, then hitting it by a minus sign doesn't change anything, right? 7 and 8, the distributive properties hold in all of Rn, or all of R2, so of course they hold for this restricted subset. 9, same thing, right? R times S times a vector in V. All right, so if we do this, R times, RS times XY is equal to R times S times XY. Why is that? Well, it holds, this equation holds in all of R2, so of course it holds in our restricted setting also. And then for the last property, 1 times x comma y is equal to x comma y. Well, that holds in all of R2, so of course it holds in our restricted setting also. Okay, that's a good place to stop. We'll see you next time.